So I would like to now also introduce our speakers from today. Philip, Anja, Herr Kohlenbach, you can turn on your cameras now quickly, and I will also introduce you to today's agenda. So first of all, Philipp Munzinger, project manager at GIZ Proklima, will introduce us to the topic of solar-powered split ACs by providing us an overview on global market trends and on the required technical components. We will then get to see some results from Professor Paul Kohlenbach from Solem Consulting of the economic assessment of PV-powered ACs, which has been conducted in our partner countries. Last but not least, Anja Wernkes, advisor at GIZ Proklima, will show us a practical example from Haiti. And afterwards, as already promised, we will have the possibility for an open discussion to address your questions. So if you have any questions during the session for our speakers, you can always post them to the chat, and we will directly address them in the Q&A session. Yeah, you can also, when posting questions, you can also give preferences to questions by, for example, giving a thumbs up. But let's start with our first speaker right away. It will be Philipp Munzinger, who is one of our GIZ Proklima colleagues. He oversees the Asian portfolio and is an expert for green cooling technologies. So Philipp, the floor is yours.
Thank you, Lara, and also from my side, a warm welcome to our today's GIZ Proklima's webinar, looking at PV-powered air conditioning systems. And yeah, happy to see more and more people joining. So I'll directly jump into the topic. Let me first introduce to you renewable cooling as such. What do we understand by renewable cooling? Generally, when talking about renewable cooling, we mean the provision of cooling to buildings or any kind of space by using natural renewable resources instead of consuming fossil fuels. And we can generally divide between two types of cooling. Well, passive cooling. Passive cooling uses naturally occurring heat differences, temperature differences. I think you all know cross ventilation being used in buildings through by opening windows using different temperature differences. So that can be classified as natural based passive cooling. But then we also have active renewable cooling solutions. There we basically distinguish between thermal renewable cooling and electrical renewable cooling. Yeah, basically in thermal renewable cooling, heat is being used typically by absorption cooling processes, and in electrical renewable cooling, we usually use electrical energy for a vapor compression cycle to generate a heat transfer. And what we have been doing now is looking at active renewable cooling solutions, combining that with our green cooling approach. That means increased appliance efficiency combined with the most climate-friendly refrigerants, and that is natural refrigerants, so that overall we will reach a minimum climate impact by applying active cooling. Here again is an overview of different solar cooling technologies. As I mentioned, basically we distinguish between thermal cooling and using heat to generate a heat transfer, and usually an adsorbent or absorbent, and electrical based cooling, where through a mechanical process of compressing the coolant, a heat transfer is being generated. And as I mentioned in our today's webinar, we specifically focus on PV powered split air conditioning split air conditioners being the most widely used air conditioning technology in buildings. So why have we been looking at this topic now for about a year? And the reason for that is because we see a couple of drivers for PV-powered air conditioning. First of all, there's an increasing demand for cooling. We can see because of urbanization, increasing middle class, also trends to work more from home office, and there's an additional need for cooling in buildings, air conditioning in buildings. Then on the other side, there's a strong need or a strong trend for more climate action in the cooling sector in contributing to countries' climate targets. That includes the Kigali Amendment to the Montreal Protocol that asks for more climate-friendly alternatives to HFCs that are still widely being used in split air conditioners, but also asking for more efficient, more carbon neutral ways in terms of efficiency and energy supply. And then we have on the bottom level here different technology trends. First of all, the increase in appliance efficiency. Over the last years, we've been observing more and more efficient split air conditioning systems being available in the market. Then there is a clear trend towards low GWP refrigerants, driven by the Montreal Protocol and regional policies like the European F-gas regulations. The need and the push to industry to develop more climate-friendly refrigerants for these systems is ongoing. Market availability is still, of course, a limiting factor. Then, of course, the price development of photovoltaic panels. Over the last decades, price of PV panels has been dropping for more than 80%. So this makes, of course, PV-powered air conditioning and from an economic point of view a more attractive application. And finally, the increasing maturity and of energy storage. Battery solutions also for household applications. So when looking at the climate impact, here on the left side, you can see a conventional split AC system being connected to a grid with, let's say, an average CO2 emission factor. We have quite high level emissions in terms of indirect energy related emissions being caused by fossil fuel-based electricity generation, but also by highly climate damaging refrigerants like HFC 410A, R32, or for HFC 32, widely being used in split air conditioning. But when transitioning to a green AC being connected to a grid, you can almost completely avoid the direct emissions part, given that propane has only a negligible global warming impact of 1 compared to HFCs ranging between 675 up to multiple thousands. But then if we combine a green AC with PV as a renewable energy source, either in an off-grid solution or in a hybrid system, combining a rooftop PV system, for example, with a grid connection, then we can again further maximize the climate impact of a cooling system in our application. So when looking at the technical components, and in our study that my colleague Carolina will post in the chat, the link to the study, you will find a lot of more detailed technical information and trends of the relevant different components. When looking at the technical components, we have PV systems where, as I mentioned, prices are falling, and therefore this technology as a hybrid or off-grid solution is getting more attractive. Then we have the split air conditioning system And there are two ways basically to apply split air conditioning. You can buy a conventional alternate current split air conditioning system that can be then used to air conditioning your building, and can be combined with a battery storage that allows you to save electricity that can be then either sold at the grid or directly be used at for air conditioning purposes. Because what we experience in many countries is that the need for air conditioning is there when the solar irradiation is quite high, because then atmosphere is heating up and the need for air conditioning is there. So at the same time, this solar irradiation creates an energy source. But then there are also DC solutions, solar air conditioners, where the direct current coming from the photovoltaic system can be directly used for air conditioning purpose. This can always be combined with different or additional technical components like inverters, which then helps us to convert direct current into alternate current, and other components that help us to stabilize and optimize the energy use in this system, like circuit breakers or power trackers. As I mentioned, further details on the different system applications can be found in our study. With this, I would like to hand over to Professor Paul Kohlenbach.
Thank you very much, Philip, for that introduction and overview on technologies and showing us some market drivers. That brings us directly to our next speaker, Paul Kohlenbach, already visible here, who will dive deeper into the topic of assessing the economic viability of solar-powered ACs with some very interesting country examples. So Paul Kohlenbach is the director of Solem Consulting, an expert in energy systems and professor of mechanical engineering and renewable energies in Berlin. Mr. Kohlenbach, the floor is yours.
Thank you very much for the introduction, and good morning, good day, and good afternoon to everyone listening out there internationally. I'm very happy to present the results of our shared economic analysis here, technical study and economic analysis of this study. It will be a rather summarized presentation today due to reasons of time. You will find all the details in the full study, which you can download with the link provided. Just a quick introduction. I just have been introduced by Lara. Thank you very much. But I'd also like to introduce Uli Jakob, who is the co-author together with me for this study. He's also professor for building technologies and renewable energy, and is my consultant colleague at Solem. The technical design we have investigated in this study was basically split between two systems shown here. On the left-hand side, we've got the hybrid system, that is a grid-connected system with 1 meter, so-called net metering. That means from the grid, you only draw the electricity required to run your house that is not provided by solar power. We don't have a battery in the hybrid system because we rely on the grid for extra supply if the sun's not shining. On the right-hand side, we've got the off-grid system. We also call it an island system because it's not grid connected. And hence it's got a battery or multiple batteries. It requires a charge controller, and then the air conditioner can either run directly on solar power or at nighttime or during cloudy periods, it can run on battery power. Those were the two main technical designs we investigated. And then we have further applied these designs to a residential building and a small commercial building. The details are shown here. Residential building, 2.5 kilowatts cooling capacity of the air conditioning unit, and the commercial building, twice that. Battery sizes and PV peak powers are have been synchronized to these designs, and we have further assumed two cases for the PV. For the air conditioning. The PV powered air conditioning is shown in this table in the first two columns, labeled green air conditioning. And then we've made a comparison against conventional air conditioning. That is our base case. The difference being the refrigerant used and the energy efficiency ratio of the air conditioning unit. So you can see that the green air conditioning units using propane as a refrigerant, R290, have an energy efficiency ratio on average over the year of 4. For those who are not familiar with that parameter, it basically says that 1 kilowatt hour of electrical energy will give you 4 kilowatt hours of cold or heat removed from your building. And then the conventional air conditioning uses R410A and an ER of 2.5 or 2.7 respectively. The other parameters here, I don't want to go into details. They're just listed here for a reason of completeness, but maybe I can draw your attention to the last line, that is the AC unit cost. We did make some cost assumptions here, basically assuming that conventional air conditioning with R410A is slightly cheaper than the propane units. And you've got the assumed prices for the AC unit in the bottom line here. All other numbers, if you're interested in those, please have a look at the study. They are explained in more detail. I don't have the time here to go to explain them all in detail. But I would like to draw your attention to another multiplier in our study, and that is climate data assumptions. You can see here a map. It basically shows China, and 3 locations have been marked. These locations are different from each other, obviously with regard to latitude and longitude, but that's not what we looked at. We looked at a parameter called global horizontal irradiation. That is basically the amount of energy you receive per square meter per year from the sun, so kilowatt hours per square meter per year. And we've chosen 3 different locations, the maximum GHI, so the highest solar energy per square meter per country, the lowest, and an average. So you can see Chongqing here is the lowest, Tingri is the highest, and Mengla is about the average. And you can see that there's quite a difference between, let's say, Tingri and Chongqing, a factor of more than 2 between those 2 parameters. And that obviously does make a difference for PV-powered air conditioning. We then have assumed a few key parameters for the PV panels and the PV system. We went for polycrystalline silicium PV panels in order to account for, global availability. In some countries, monocrystalline is dominating the market, obviously, but we've gone for the slightly less efficient panels here. All PV panels were oriented due south, so pointing exactly to either the equator from both sides of the equator, and the panel slope was optimized per latitude. So to summarize the modeling that we've undertaken, we had 2 building types, residential and commercial, 2 grid connection options, hybrid and off-grid, 3 locations per country, minimum, average, and maximum GHI, and 13 countries. And that was 156 simulation runs. What was the outcome of the simulation runs? It was the solar yield per year, and hence the air conditioning operation time per year per location, and we did combine that with air conditioning load patterns per building type and per country, and in the end, what we calculated was the solar fraction So that is the ratio of solar operated air conditioning to the total air conditioning demand per year. With these technical outcomes, so the modeling results, we then went into our economic analysis. We investigated two economic parameters: the levelized cost of electricity, shown on the top-hand side, on the right-hand side, top right-hand side here, and the net present value in PV, shown in the middle on the right-hand side. Levelized cost of electricity is basically the average cost over an assumed period of time, including interest rate and the investment cost. So it's operational and investment cost averaged over your assumed lifetime of plant or operational time, which in our case was 20 years, and the interest rate was 5%. Net present value is taken into account any earnings from your PV system, which we had to include, obviously, because in some countries we investigated, there was a feed-in tariff present. And so the hybrid option, which was grid connected, in the hybrid option, feed into grid was possible. And if a feed-in tariff was present in the country, that would the owner of the system, that would give the owner of the system some income. And so the net present value was calculated using earnings and operational cost, as well as investment cost. We have included a consumer price index of 1% increase per year, and we've made some assumptions on the operating expenditure as a percentage of capital expenditure, CapEx. So the focus of these economical calculations was to answer the question, is it economically viable to invest into a PV plant and an air conditioning unit using R290 to provide cooling for your house or your small commercial building? This question we wanted to answer. We have produced a lot of results, and I've summarized them for you in this table. We have listed here the 13 countries, and then we've got the 4 options, the building options combined with the technical grid connection options. And a full tick basically means that the net present value of the green air conditioning is higher than of the base case. So in that case, it's favorable from an economic point of view to invest into PV panels, propane air conditioner, and run them for 20 years, and it will cost you less than the base case R410A no PV scenario. A tick in brackets is close to economic viability. It basically means that the 2 net present value numbers of propane and conventional refrigerant-based air conditioning are so close to each other that they are within the sensitivity range of the base case scenario. And the sensitivity range is basically the difference between our 3 locations. So depending on your solar irradiation per country, we have a range of possible net present value figures. And if the tick here is in bracket, it means that PV-powered propane-based air conditioning is so close to the base case that it really depends on where you are in the country to make a difference. Okay, coming to the conclusion, for a residential house, typical single-family residential house in the 13 countries, the hybrid option, grid connected, green PV-powered air conditioning is almost feasible for all countries. We have 2 exceptions, that is Ghana and Vietnam. So 11 out of 13 countries, there is an economical advantage if you run your air conditioner on PV power. Off-grid, we have a slightly less good option here. It's only feasible in 5 out of 13 countries. That is basically due to the higher cost here. You have to purchase an extra battery for the off-grid option, and there is no possibility to feed into the grid. That means you don't get any earnings from a potential feed-in tariff. So Costa Rica, Iran, Grenada, Philippines, and Thailand is where the off-grid options are still feasible, 5 out of 13. If we go small commercial, the hybrid option is 10 out of 13, where it's economically feasible. Again, Ghana, Colombia, and Iran, it is cheaper to run the base case scenario without PV power. And off-grid small commercial, we only have 4 out of 13 countries. Again, the cost is dominating here. It is feasible in China, Grenada, Kenya, and the Philippines. And that takes me to the end of this very short summary. If you have any questions, we can certainly talk about it in the Q&A session. And I would also encourage you to download the study, because I would think most of the questions will be answered by downloading and reading the full study. So thank you very much for your attention.
Thank you very much, Mr. Kulmbach. Yeah, that was very valuable insight on, especially on the financial advantages of PV-powered green ACs in several countries. And but I agree with you. There is much more information, and all included in the study. We will provide you the link during the Q&A session. So in our next input, we will look at a specific case in a hospital in Haiti. Anja Wernkes is one of our colleagues and holds a master in engineering and policy analysis. We're looking forward to find out how Haiti implemented solar cooling. So Anja, the floor is yours.
Thank you very much, Lara, and also hi to everyone. So yeah, I'm happy to present some practical insights from a pilot project from Médecins Sans Frontières, or in English, Doctors Without Borders, in Haiti. And I would first like to start with some background. MSF needs air conditioning to cool medical facilities and for cooling in offices and residences. They often use fixed speed split ACs, but increasingly more efficient variable speed split ACs. But these are often powered by generators and not connected to the grid, because their projects are often in remote locations. These figures here are based on rough estimations from MSF. So AC use makes up around 35% of MSF's total fuel consumption. This accounts for about 3 million euros per year and about 6,000 tons of CO2 equivalent emissions per year, only the indirect emissions from electricity consumption. So given this background, in 2018, MSF first piloted the use of PV-powered ACs at a hospital in Haiti. So they looked at 3 different applications and installations covering different cooling needs. The first was 24 hours use in an operating theater, the second daytime cooling in consultation rooms, and the third nighttime cooling in residential rooms. And in each of these 3 cases, they looked at different installations. So in the operating theater, the AC was connected to PV panels and a diesel generator. In the consultation rooms, the ACs were only connected to PV panels and powered by PV only. And in the residential rooms, they also used battery backup. Looking at the equipment, the project team purchased AC units from a Chinese manufacturer to replace the conventional ACs with more energy efficient ACs using R410A as refrigerant. So these were not green ACs in this pilot project, because their focus was on using solar power and not on natural refrigerants. The yeah, these were hybrid units, so they could switch between AC and DC power mode. And each PV panel was then connected, each AC unit was then connected to 4 PV panels with a total maximum power output of a bit more than 1 kilowatt. For the battery backup case, they used a large lead-acid battery bank because it was available at the hospital with a capacity of 1,415 ampere hours. So this was intentionally oversized for longevity reasons. And they didn't consider other battery types in this project because the aim was to minimize reliance on batteries, but this one was available there. Yeah, coming to the findings. So first of all installations are working well, and MSF is still conducting more analysis on energy performance. And in terms of cooling supply, the PV-powered AC units without any backup generated enough cooling for daytime use. The hybrid ACs covered the remaining cooling needs using generator power. And the AC with battery backup for nighttime use also worked well in this case, but it also became clear to them that large battery banks would be required unless AC operation is very limited at night. Second, they also achieved significant cost savings. So of course, this depends on diesel prices and equipment costs. But just to give you an example, for a small room in a well-insulated building, such as the hospital in Haiti and in Haiti's climate, the savings were around 450 euros per year compared to a less efficient and generator-powered AC. In the battery backup case, of course, costs are significantly higher. And third, in our study, we also estimated climate benefits for the different cases. The direct emission savings per AC unit were between 1 and 2 tons of CO2 emissions per year due to, on the one hand, higher energy efficiencies, and on the other hand, replacement of diesel generators by solar power. And then we also looked at the potential direct emission savings that could be achieved by using green ACs, what Philip already mentioned earlier. And these were around 500 kilograms CO2 equivalent emissions per year for one AC unit. But again, this is only a very brief overview, and you're very welcome to have a look in our study for more figures. And yeah, coming to the conclusion, so this pilot project showed the great potential of PV-powered ACs, and especially the hybrid systems and for daytime AC operating times. Up to now, MSF has installed more than 150 solar-powered ACs in Malawi, South Sudan, Bangladesh, and other countries. But yeah, some barriers remain for a larger scale uptake of the technology. So some are listed here. For instance, the limited local availability of key components, as well as complete solar AC solutions, especially in remote areas, remains a barrier. Then also the lack of awareness among end users, but also the lack of trained technicians and higher upfront costs compared to grid-powered or generator-powered solutions. And yeah, finally, as Philip also mentioned at the beginning, it's key to improve passive cooling measures to reduce cooling needs in the first place, such as good insulation of buildings, which then also make solar-powered cooling more feasible. And yeah, with this, I just also wanted to thank the team at MSF for providing us with all the insights on their project. And yeah, I'm looking forward to the Q&A session.
Thank you very much, Anja, for your input and yeah, that very, very interesting case study and seeing some results on site. Yeah, this brings us to our Q&A session. So I already checked the chat and we have fortunately received a few questions already. Thank you for those. I would just like to start the Q&A session with a short poll. For that, I will post a question in the chat, or it's rather a poll actually where you can vote, which should be seen now. And yeah, you can just vote whether you already have experience with PV-powered AC systems or not. Yeah, just interesting for us to know whether we have some more experts here in the round with on-site experience and maybe also experience they would like to share with us in this discussion. So we have 2 with experiences. Maybe you can also type in the chat where, in which country or in which way you have collected those experiences, and many without experiences. But yeah, that is also what the study is for, to give first insights on how this could look like and the advantages of it. Great, thank you for that. And then we will start right away with a few of the questions from the chat. I will just start from the beginning. So we have received a quick question on the reasons for the exceptions in the case of Ghana. So Mr. Kuhnbach, on your slide with the table, there were no, I think, ticks for Ghana. So maybe you can just quickly explain that.
Yep, I'll do my best. Ghana, as well as the other 12 countries, we have made assumptions for the local electricity cost, for the air conditioning hours, a potential feed-in tariff if present, and the assumptions for the investment costs have also been adjusted per country. The only constant number was the cost for air conditioning unit, which was the same for all countries. So in Ghana, we would have to look at the input parameters for this country. And my suggestion would be, if you have a look at the study, because we have listed all input parameters there, before we try and go into detail here. So if you don't mind, the study will probably answer this question. My guess would be that we have a rather low local electricity cost combined with low air conditioning load. And that obviously doesn't make for such a good economic case. But it would probably take us a little too long if we look up every country individually now. So if we could agree on that. If you have any questions after you've read the study, feel free to send me an email.
Okay, great. Yeah, thank you. I think this also addresses quite well the comment from Anders from China that it's always good to have the actual spreadsheets and the data so that you can also probably make adjustments in case of any changes needed. So yeah, from Anders, we also have a question that the study looked at the sunniest and least sunniest locations with regard to whether there is significant population or energy demand there. Based on the examples of China, where rural Tibet and Yunnan would seem insignificant from an energy demand perspective. Mr. Kuhnbach, this is also a question for you.
Yeah, that is true. The assumptions we have made were, best, worst, and average solar irradiation, because that is one of the significant input parameters for the economic results. What we haven't done is combined solar radiation potential with population. That's a different overlay. which obviously could be well done in a future analysis. But for this study, we haven't done this. We haven't used this approach, well, mainly for reasons of resources. We wanted to do a first potential analysis in order to gain a sensitivity, for the parameters. But that could be a very good second step to look at, the population distribution and then combine that with the solar radiation. So thanks for that. Thanks for that idea. I think that is something we could do in a second step.
Okay. Thank you very much. Then we have another question from Denise from Thailand. So do you also have an insight on for which cases mini chiller for cooling plus combination with PV could be more efficient instead of smaller split ACs?
Mini chiller, if I hope I understand correctly, a chiller for me is something that generates chilled water instead of conditioned air, right? So if I get your question correctly, you're asking whether chilled water, let's say for commercial building use, is more efficient instead of split air conditioning units. The answer is that depends, obviously. It depends whether you've got an existing building. Retrofitting chilled water pipes in an existing building is very costly and would not be economically advantageous. If you have a new building that is going to be built and you can integrate chilled water piping and, let's say, chilled ceiling panels or fan coils in the building, that might be an option. Chillers are generally slightly more efficient. And typically, the comfort in rooms that are conditioned with chilled water is perceived a little better from the user than chilled air. But it really depends on your case. There's no general yes or no answer to this question.
Yeah, thank you very much. Also, question to Philip, and I think you already addressed it a bit in the chat, but I would be curious in knowing whether GIZ Proklima has some projects in the field or planned projects for the implementation of a case study like this.
Thanks, Lara. As I mentioned, we have been increasingly looking into the combination of solar energy, especially PV, and green cooling, not only in terms of air conditioning, but also in terms of refrigeration. And we have another study published by the Green Cooling Initiative looking at solar-powered cold rooms. And I think this is what we experience is that this market is still at its infant stages. There are not really large market shares, and although I think the technical and economic potential is quite huge, as the study shows, especially because prices of different components, not only PV but also AC systems and battery solutions are going down. Our upcoming project, Cool Contributions 2, will look into this topic or during its implementation. Also, pilot projects are planned to gather more information. We're discussing pilot projects in Grenada, potentially also the Philippines and other countries. So this is a topic that we will continue to work on together, further practical experience to be shared with you.
Thank you, Philip. And regarding the case study, Anja, that you have presented, do you know whether there has been some upscaling of that project case after the successful implementation or a multiplication of that kind, maybe in the region as well?
Yeah, thank you for the question, Lara. I think I also mentioned it on my last slide that MSF is really trying to install more and more solar-powered ACs in different countries. So I'm not aware of any more projects in Haiti, but they have installed solar-powered ACs in Malawi, South Sudan, Bangladesh, and others, and are still planning to implement more because they saw such a huge potential to reduce diesel consumption and costs, as well as their carbon footprint. So it was really a successful pilot project and more to follow.
Okay, great, thank you. Yeah, I think it's always interesting to have some first-hand and experiences and direct impacts as well. I think we have time for one or two more questions for you, Mr. Kohlenbach. Did the study give an attention to whether the PV was available at the times when the cooling was required, or whether cooling was required when PV was available, or whether the air conditioner could ramp to the available PV power rather than cycle on and off?
Yeah, certainly. That's a very good question. And yes, the study did deliver those results. The modeling was a detailed 15-minute interval modeling. So we had roughly 35,000 time steps per year. And the interaction between available solar power, air conditioning load was matched for each of those 15-minute time intervals. We have to differentiate here between the hybrid option, grid connected, and the off-grid option. In the grid connected option, if there was no solar power available, then obviously the grid would supply the power required. In the off-grid option, if there is no solar power available, then the battery would be used. If the battery was empty, the air conditioner would shut off. So the ramping that you mentioned is only, has always been done according to the load. But if there was no solar power available, then in the hybrid option, the grid would provide the power. In the island mode, the battery. And we have for each run, for 156 runs for each run, we have the breakdown of these times, certainly. But we haven't put them in the study because, that would probably blow up the volume and make the study much longer. I'll be happy to provide, if you send me an email, I'll be happy to provide individual questions material here. If you want some breakdowns for specific countries, just send me an email, please.
Great, thanks. We have time for one more question. There are actually two more questions, but maybe Mr. Kohlenbach, the last one is addressed also to you. You can also answer it in the chat, or we can answer it afterward. But Anja, first of all, compliments to the great case study in the chat, and the question: is there any data on the average number of hours the system was able to run during daytime, and the number of hours the system was depending of other power? So whether you have that data, or if the data is available.
Yeah, thank you also for the question. I think we didn't include the exact number of hours in the study, but I have some more data on these numbers, and I'm also happy to provide them to you by email. But then there's not yet complete data on the energy performance and the energy supply for each of the cases. So especially in the hybrid case, where there was a switch between generator power and solar power, MSF didn't completely monitor all the data yet. These analyses are still ongoing. Hope we can follow up on this later.
Thank you very much, Anja. Yeah, and if you have any questions also arising after this session, please just contact us. Also, maybe directly on the study we will provide, or we have already provided the link in the chat. So thank you very much for all your questions, which brings us also to our few last slides now. So thank you to all the speakers as well for your valuable input, and to all the participants for showing your interest in this webinar. So what you see on this slide is the recently published study on PV-powered ACs in buildings, which can be downloaded on the Green Cooling Initiative website. You have also the link in the chat. But yeah, we will also share the presentation, and you can use the QR code or the link provided in here. Furthermore, we have included another link to a publication on solar-powered cold rooms, which is also another sector with very high potentials for using solar energy. The link is also within the slide. This is just an overview of the members of our network from the Green Cooling Initiative. Yeah, I would like to invite you to have a look at the website of the Green Cooling Initiative, where you can receive more information around related topics, and also become a member of the network of public and private actors and pioneers of green cooling around the world. And by becoming a member, you will also be updated on any new developments and invited to events like this one. Yeah, actually now we have a few more minutes, but I think, like, looking at the chat again, because of course I would like to have all your questions answered, but yeah, thank you, Mr. Kuhnbach, for directly answering in the chat now. And I think we covered all questions. So I would say, yeah, a few minutes ahead of time would close that meeting. Thank you very much for your attention, and yeah, sharing all your interest, and yeah, enjoy reading this very interesting study.
Thank you. Bye-bye.
Thanks for your interest. Bye-bye.